US Physics Olympiad year 2018 final round USAPHO. This examination consists of two parts. Part A has 3 questions and is allowed 90 minutes. Part B also has 3 questions and is allowed 90 minutes. Problem A1. Question A. Suppose you drop a block of mass m vertically onto a fixed ramp with angle theta with a coefficient of static and kinetic friction μ. The block is dropped in such a way that it does not rotate after colliding with the ramp. Throughout this problem, assume the time of the collision is neglectable. First, suppose the block's speed just before it hits the ramp is v and the block slides down the ramp immediately after impact. What is the speed of the block right after the collision? Second, what is the minimum μ such that the speed of the block right after the collision is 0? Question B. Now suppose you drop a sphere with mass m, radius r and the moment of inertia beta m r square vertically onto the same fixed ramp such that it reached the ramp with the speed v. First, suppose the sphere immediately begins to roll without slipping. What is the new speed of the sphere in this case? Second, what is the minimum coefficient of friction such that the sphere rolls without slipping immediately after the collision? Problem A2. For this problem, graphical answers should be drawn on the answer sheets, graphs provided. Supporting work is to be written on blank answer sheets. Incorrect graphs without supporting work will receive no partial credit. The current I as a function of voltage V for a certain electrical device is next one, where Q is the magnitude of the charge on an electron, QB is Boltzmann's constant, and T is the absolute temperature. I0 and V0 are non-zero positive constants. Throughout this problem, assume low temperature values KBT much less than QV0. Question A. On the answer sheets, sketch a graph of the current versus voltage for low temperature values KBT much less than QV0, clearly indicating any asymptotic behavior. Shown is a schematic for the device. Positive voltage means that the electric potential of the left-hand side of the device is higher than the right-hand side. For this device, I0 equal 25 microampere and voltage and V0 equal 1 volt. Below is a circuit made up of these elements. The voltage supplied the circuit is sinusoidal. VAB equal VA minus VB equal VS sine omega t, and is also shown on the answer sheets. The resistance is R equal 5 ohm and the S equal 5 volts. Question B. Sketch the potential difference VCD equal VC minus VD as a function of time on the answer sheet. For your convenience, VAB is shown in light gray. Assume that VAB has been running for a long time. So that's the answer sheet. Now a capacitor is connected to the circuit as shown below. The capacitance is 50 microfarad. Question C. Sketch the new potential difference VCD equal VC minus VD as a function of time on the answer sheet. For your convenience, VAB is shown in light gray. Assume that VAB has been running for a long time. So that's the answer sheet. US Physics Olympiad year 2018 USAPHO. Problem A3. A vacuum system consists of a chamber of volume V connected to a vacuum pump that is a cylinder with a piston that moves left and right. The minimum volume in the pump cylinder is V0 and the maximum volume in the cylinder is V0 plus delta V. You should assume that delta V much less than V. The cylinder has two valves. Inlet valve opens when the pressure inside the cylinder is lower than the pressure in the chamber, but closes when the piston moves to the right. The outlet valve opens when the pressure inside the cylinder is greater than atmospheric pressure PA and closes when the piston moves to the left. A motor drives the piston to move back and forth. The piston moves at such a rate that heat is not conducted in or out of the gas contained in the cylinder during the pumping cycle. One complete cycle takes time delta T. You should assume that delta T is a very small quantity, but delta V over delta T equal R is finite. The gas in the chamber is ideal monatomic and remains at a fixed temperature of TA. Start with the assumption that V0 equals 0 and there are no leaks in the system. Questions. Question A. At time t equals 0, the pressure inside the chamber is PA. Find an equation for the pressure at later time t. Question B. Find the expression for the temperature of the gas as it is emitted from the pump cylinder into the atmosphere. Your answer may depend on time. For the remainder of this problem, 0 less than V0 less than dV and much less than V. Question C. Find an expression for the minimum possible pressure in the chamber P minimum. US Physics Olympiad year 2018 USAPHO. Problem B1. The electric potential at the center of a cube with a uniform charge density ρ and the side length A is approximately 0.1894 ρ A square over epsilon 0. You don't need to derive this. For the entity of this problem, any computed numerical constants should be written to 3 significant figures. Question A. What is the electric potential at the corner of the same cube? Write your answer in terms of ρ A, epsilon 0 and any necessary numerical constants. Question B. What is the electric potential at the tip of a pyramid with a square base of side length A, height A over 2 and a uniform charge density ρ? Write Write your answer in terms of rho A, epsilon 0, and any necessary numerical constants. Question C. What is the electric potential due to a square plate with a side length A of a uniform charge density sigma at a height 8/2 above its center? Write your answer in terms of sigma A, epsilon 0, and any necessary numerical constants. Question D. Let E as a function of Z be the electric field at the height Z above the center of a square with a charge density sigma and the side length A. If the electric potential at the center of the square is approximately 0.1281 A sigma over epsilon 0. Estimate A on distance A/2 by assuming that E from Z is linear in Z for 0 less than Z less than A/2. Write your answer in terms of sigma A, epsilon 0, and any necessary numerical constants. US Physics Olympiad, year 2018, USAPHO. Problem B2. In this problem, use a particle-like model of photons. They propagate in straight lines and obey the law of reflection, but are subject to the quantum uncertainty principle. You may use small angle approximations throughout the problem. A photon with a wavelength lambda has traveled from a distant star to a telescope mirror, which has a circular cross-section with radius big R and the focal length f much greater than R. The path of the photon is nearly aligned to the axis of the mirror, but has some slight uncertainty delta theta. The photon reflects off the mirror and travels to a detector where it is absorbed by a particular pixel on a charge-coupled device CCD. Suppose the telescope mirror is manufactured so that the photons coming in parallel to each other are focused to the same pixel on the CCD, regardless of where they hit the mirror. Then all small cross-sectional areas of the mirror are equally likely to include the point of reflection for a photon. Question A. Find the standard deviation delta R of the distribution for R, the distance from the center of the telescope mirror to the point of reflection of the photon. Question B. Use the uncertainty principle delta R multiplied by delta P greater or equal to reduced Planck constant over 2 to place a bound on how accurately we can know the angle of the photon from the axis of the telescope. Give your answer in terms of R and lambda. If you were unable to solve part A, you may also give your answer in terms of delta R. Question C. Suppose we want to build a telescope that can tell which high probability whether a photon it detected from Alpha Centauri A came the left half of right half of the star. Approximately how large would a telescope have to be to achieve this? Alpha Centauri A is approximately 4 by 10 power 16 meters from Earth and has a radius approximately 4 by 10 power 9 meters. Assume visible light with a lambda equal 500 nanometers. US Physics Olympiad year 2018, USA PHO, problem B3. Radiation pressure from the Sun is responsible for cleaning out the inner solar system of small particles. Question A. The force of radiation on a spherical particle of radius small r is given by formula F equal PQ P r square, where P is the radiation pressure and Q is a dimensionless quality factor that depends on the relative size of the particle r and the wavelength of light lambda. Throughout this problem, assume that the Sun emits a single wavelength lambda maximum. Unless told otherwise, leave your answer in terms of symbolic variables. I. Given that the total power radiated from the Sun is given by Ls, find an expression for the radiation pressure at distance r from the Sun. II. Assuming that the particle has a density ρ, derive an expression for the ratio F radiation over F gravity in terms of Ls, mass of Sun ms, ρ, particle radius r, and the quality factor Q. III. The quality factor is given by one of the following. Consider the three possible particle sizes, which is most likely to be blown away by the solar radiation pressure. Part B. The Poynting-Robertson effect acts as another mechanism for cleaning out the solar system. I. Assume that a particle is in a circular orbit around the Sun. Find the speed of the particle v in terms of ms, distance from Sun r, and any other fundamental constants. II. Because the particle is moving, the radiation force is not directed directly away from the Sun. Find the torque tau on the particle because of radiation pressure. You may assume that v much less than speed of light c. III. Since tau equal dl over dt, the angular momentum L of the particle changes with time. As such, develop a differential equation to find dr over dt, the rate of change of the radial location of the particle. You may assume the orbit is always quasi-circular. I4. Develop an expression for the time required to remove particle size r about 1 cm and density 1000 kg per meter cubic, originally in circular orbit at a distance r equal r Earth, and as numbers below to simplify your expression. Some useful constants include